Well, good morning, pre-calculus students. Looks like we are ready to start with 9.4. And so we are going to be looking at series. And for some reason, we're a little blurry here. Let's see if I can get it to zoom in. There we go. That's better. So with series, they are actually very, very similar to sequences because they really contain a sequence. So when we go to define what a series is, it's going to start with the idea of a sequence. So it contains that. So here's our definition. It is essentially the sum of the terms of a sequence. So if you imagine you've got your sequence, you've got your ordered list of numbers, and then instead of just having a list of numbers, now you put plus signs between each one and you add them up. That's a series. So a series is just a big old sum of a bunch of things added together, and specifically they're the terms of a sequence. So let's start talking about these things. These actually become much more mathematically useful than the series do, but than the sequences do. But if you don't know a sequence, you won't understand a series because a series requires a sequence. So let's start talking about this in terms of notation. We need some ways to depict these things a little bit easier. So here we're going to look at some notation. So the first thing we're going to see for notation is, let's look at a given series here. So this series, notice it is a sequence of numbers, 2, 4/3, 8, 9, 16 over 27, 32 over 81. And it is this sequence of numbers, but notice there's pluses between each. So it's not just a list of numbers, we're actually adding all these numbers up. Notice it's also an infinite sequence, an infinite series here, because we don't have an end. Okay, so we would like to be able to write this some other way other than to go and list it as having to list all these terms like this. So what we do is we have the following notation. The first thing that we do is we use what is called a sigma. It is basically a capital Greek S. A lot of people will say it looks kind of like an E. It does look kind of like an E, but it's a capital Greek S to stand for the idea of a sum. So down here we have the beginning index number. So here we start with K equal to 1. That's where we're going to start our index number. And then we're going to go up by 1 each time. And this tells us where we're going to stop. And in this case, we're not going to stop. It's going to go to infinity. And then what we see here is our rule. This is our explicit rule for the sequence. Notice if we look at this sequence here, we see the sequence of numbers. It's a geometric sequence. We're multiplying by 2/3 each time. So here's my G1. My first term is 2. Here's my common ratio, 2/3. And I'm raising it to the K minus 1 power. Now, if I want to raise it just to the K power, I could start this at 0. That's another way to do it. It really doesn't matter so long as you make sure that when you start with whatever index number you start with and you start plugging in, it actually does yield this sequence here. So an alternative definition of this would be the series K equals 0 to infinity of 2 times 2/3 to the K power. That would also be the same. All right. So let's look at our general term. Our general definition is going to look like this. So we have K equals 1 to N. N is the ending, that's the number of terms that we have. If we start with 1 and we go to N, then we have N terms. Okay, so for instance, if this is 10, going from 1 to 10 is 10 terms. Our A of K, that is our definition of our sequence, like that. And so here we have this. So this is where N is the number of terms, and A of K is the explicit definition of the sequence. So it gives us the value of the K term. Okay, so if K is 1, it gives us the value of the first term. If K is 3, it gives us the value of the third term, etc. All right. So now the key is we want to be able to find sums. Obviously, one way to do it is to list out all the terms and see what it adds up to. But that can be kind of a pain. Because if we want to add this up here, let's look at this situation. So we have this series, 1 plus 2 plus 3 plus 4 plus 5, all the way up to 100. And so written in summation notation, we call this summation notation. We have k equals 1 to 100, and each term is just k. So when we plug in that, it gives us the value of each term. Our rule there is very simple. So the question is, what is this sum? What is that up to? Well, one thing we could do is we could literally write out all 100 terms and simply add them up. But even with a calculator, we know we don't want to do that. We don't want to add up 100 different terms. So we want to look for patterns and ways that we can do this that will be more efficient. So here's what we're going to notice. We're going to notice that if I was to rewrite this exact same series starting at 100 and going down to 1, notice the sum of each of these pairs of terms is each going to be 101. So if I add up this column here, each time it's going to be 101. So the whole thing, if I add this up, there are 100 terms, and each pair here is 101. It's going to be 100 times 101. But that's the sum of two of these. So if I take that 100 times 101 and divide it by 2, I would get my sum of 5,050. Well, this gives us insight into how we can do this, because this is an arithmetic series. And this will basically work with any arithmetic series. So we come up with a formula for this, and here's our formula. So if this is an arithmetic series, this is defined to be a general definition of an arithmetic sequence there, then we know that that sum is going to be equal to the sum of the first and the last term. That would be the 1 and the 100. That gets us our 101. And we multiply it by the number of terms. That would be our 100. Remember here we saw it was 101 times 100. And then we have to divide by 2. So we can simply express it like that, and that becomes our rule for finding the sum of an arithmetic sequence. So any arithmetic sequence will work this way. Or here's another way you'll see it written. This is the way your book shows it. Now this is the way, if you don't want to take the time to find the first and the last term. Notice this here, we don't have to find the last term. All that we have to know here, we have to know the first term, we have to know the number of terms, and we have to know our rule here. We just have to know our common difference. That's all we have to know. So that this works here if we don't find the last term. If we want to find the last term, then this one will work. Simple enough. So let's go ahead and let's look at what happens if it's geometric. So notice this A of k I wrote to designate. That was if it was arithmetic. Well, what if it's geometric? Well, if it's geometric, it's going to look like this. It's going to look like our first term times 1 minus r to the n power, where r is the common ratio, and of course n is the number of terms, divided by 1 minus r. So that's if it's geometric. So let's look at applying these formulas. So we want to add this up. The first thing to do is to find out, is it arithmetic or is it geometric? And we can see pretty quickly that what we have here is we have a common difference. We're adding 6 every time. So we can either use this with our common difference, knowing our first term is -7. The challenge here is this one, we don't really know necessarily. We have to figure out the number of terms. That's really the challenge, is to figure out the n that goes there. So one thing you can do is you can simply define. So what I did here is I went to get an explicit definition here for my sequence. So -7 was my first term. My common difference was 6 times n minus 1. Simplifying this down, I get this form right here. So now I have to find out, how many terms do I have? Well, I need to find out the difference between my first term and my last term. So I'm finding the difference here. So I'm taking my last term and I'm subtracting my first term. So notice my difference is 60. And I'm going up by 6 each time. So what it means is I actually have, we have to be careful here. That means I have 11 terms. Because I have to add 6 10 times. But notice what that does. I have my starting term, and then I add 10 times, I add the 6 to it. So that gives me a total of 11 terms. It gives me my starting term plus the next 10 terms that I get when I add 6. So I actually have 11 terms. So when I go to express this in summation notation, I know that I have 11 terms. And I can always check this. If I put 11 into this, I better get my last term. And notice if I put 11 in here, what I would get for my last term is I would have that 66 minus 13, which is 53. So that does work for getting my last term. So I do have 11. I can always check it. So now, actually on this one, they didn't want me to find the sum. They just wanted me to get it in summation notation. So there, what I had to do is I had to make sure I had my formula, which I found, and then my number of terms. So number 15, this does want me to find the sum of the geometric series here. So they give me my first term, they give me my common ratio, and they give me my number of terms. So I can just go right up here to the formula, and I've got everything that I need. So I'm going to go ahead and plug in. My g of 1 is 42. So my sum here, that's s, is equal to 42 times 1 minus, and I've got my ratio 1/6 to the 9th power over 1 minus 1/6. And at this point here, we're not going to expect you to do this without a calculator. So go ahead, plug into your calculator, and you get 50.399995. Okay. So you're going to have to go out a few decimal places to indicate the amount of accuracy that you're going to have here, because these things are actually getting, you have to go out a number of decimals because they are really approaching particular values here. Okay. There's your homework. 9.4, 1 through 22 all. So you're either going to have to express things in summation notation or essentially find the sums. So I hope that goes well. The next video will be next week. And we are pretty much quickly making through with it. Probably by the end of next week, we'll be pretty close to being done with stuff, and then we can start reviewing. We probably will actually, we'll be pretty close. Next week, we won't be all the way done. We will be into chapter 10, and we'll probably finish up with chapter 10 the first couple weeks. And then the end of the next week, we will have our last test. And our final test, remember, is not a true final. It's just going to cover these last 3 chapters that we've done, chapters 8, 9, and 10. So that kind of gives you an idea where we're headed. Hope things are going well. And go ahead, email me something, or put it on Google Classroom if you have a question. If not, we will have Zoom sessions next week where you can ask questions and get help. Okay, hope things are going well.